Okay, so hello everyone. Today I'm going to give a talk on some of the work that I've been doing to describe ontologies in terms of category theory. So I just want to preface this talk with a number of things. So first of all, this is going to be, I don't know, maybe my sixth time explaining this sort of thing. And what I've found is that the details of this theory end up being really complicated and at some points very combinatorial. And on top of that, I would like it to extend towards people who don't necessarily know any category theory. So with that being said, this talk is sort of an experiment for me in explaining this in the most intuitive way possible and trying to ignore as much of the categorical formalisms as I can. Now, that being said, I think that I am somewhere in between formal and informal. So it might just not achieve either. And well, hopefully there's some intuition here and some formality so that we can all sort of get a grip on what I'm talking about. The second part of this talk will be some more, some newer ideas that I've had about how to apply these ontologies, these hierarchical ontologies, towards reasoning, towards understanding subjects, towards understanding concepts. And so those ideas, and I'll let you know as soon as I haven't really been able to formalize those ideas yet, those ideas are rather new, and so it's maybe hard for me to actually describe them in a talk setting like this. But that being said, the first half of this talk, I've given the talk several times, and actually, if you look at my website, so here's my website, which is rather new. So it's my GitHub account, which is .github.io. There is a talk page, and on that talk page, there are two other talks, one at Johns Hopkins, which I gave last semester, and another at the New York Category Theory Seminar, which I gave about a month ago. And these talks are a lot more formal. So if you want to see more of the formalism before I actually publish this work, which hopefully that's soon, you can look at those talks. Okay, so without further ado, let me get started on what I'm talking about. So what I want to talk about is the distinction between logical construction and ontological construction. So actually, the one other thing that I wanted to preface is that I don't know how much my mic is going to be cutting in and out or whatnot. I've heard some complaints. So I'm going to try to write as much as I can, and that might slow the talk down, but I think it'll be good for the video and for whoever's watching. And by the way, it seems like there's only 5 people here right now. So at any point, and seriously any point, whenever you feel comfortable, you can stop me and ask a question or share an idea. Okay. So we were trying to talk about the distinction between logical construction and ontological construction. So let me give you a picture about what those two things are. So the way that we construct objects in mathematics is via logical constructions. So just to give you an idea about what I mean, well, for example, there's, well, the axioms of set theory. So I'm not going to go really that deep into it. But if you wanted to construct a set, you would be using Zermelo-Franco, for example. And now on top of that, another example I can give is a space. Okay, so if I give you a space X, it is a collection, two things. It's going to be a set X and a subset tau in the power set of X. Okay, and then that satisfies certain properties, but I'm not going to get too detailed here. Okay. So this would be like a logical construction. If I was going to be talking about a particular space X, I would be giving that set, and I would be giving that subset, and I would also be checking that these axioms that I didn't list are satisfied. So on the other hand, with category theory, we start to see more ontological constructions. So ontological constructions. So what an ontological construction might look like is a construction from properties relating to an entire, to the entire ambient category that something lives in. Okay, so for example, we might talk about an M in manifolds. And the way that we describe manifolds is via open sets that cover our manifold M, and also via isomorphisms from those open sets into balls that lie inside of some version of the real numbers, so some dimension of the real numbers. Okay? So the understanding of a manifold is, on one level, a logical construction. I would have to be giving a set and potentially the open sets of the manifold when considered as a space. But to consider it as a manifold, I also want to view the open sets and, moreover, the isomorphisms from those open sets into the real numbers. Other ontological constructions, so other examples, include universal properties. Okay, so for example, we have like the product of a bunch of spaces, or the kernel of a homomorphism, or the co-limit of some diagram. Okay, and the way that these are defined is not as, well, logically this would be defined as maybe some tuples, but ontologically this is defined by a universal property. Namely, we have this product of xi, and we have a bunch of projections into the xi's, and moreover, for any other z that satisfies this sort of thing, let me try this out and zoom in a little bit more.
Yeah, that's much better.
That's good? Okay.
Yeah, thank you.
This way, I think maybe people who are not rotated in my direction will have the correct orientation. Okay. So just to revisit what I was talking about, there is the logical construction of the product, but then there's the ontological construction. Okay. So just to give maybe some more examples, and I'll move on. Properties that are purely categorical. So for example, epimorphism or monomorphism or isomorphism, or maybe even things like weak equivalence, etc. these are all ontological properties. So if I wanted to check if something is epimorphic, I would have to check it against a ton of other maps, okay? Not just the objects for which the epimorphism is going into and out of. The logical side of this would be like surjection. The ontological side is epimorphism. Okay. Now, what we have in category theory is a very basic lemma that like everything is based on, is the Yoneda lemma. Okay. And so for those of us who maybe missed my preface, I'm going to be as loose as possible with the categorical formalisms here. So what the Yoneda lemma seemingly does is bridge together the logical and the ontological. So you might ask what I mean by that. Well, the Yoneda lemma, what this is saying in sort of an intuitive sense, is that the isomorphism classes, so the iso classes of X are determined by the maps into and out of X, okay? And for those of you who want to see what this means more formally, well, what the Yoneda lemma does, it has a Yoneda embedding, and it sends X to this functor as follows. And for those of you who don't know what I'm talking about, don't worry. But this functor is full and faithful, and it's also reflexive, meaning that any isomorphism of functors is going to have to come from an isomorphism of the objects, okay? So this is seemingly bridging together the logical and the ontological, but actually it's not. So it's not really a bridge, and that's because giving an isomorphism class of X is not, explicitly not, giving a construction of X, okay? So just to detail this point a lot more, let me do a little thought experiment, okay? So we're gonna play a game, all right? So here's the game. So we have a game. Okay, so I'm going to give you an object, X, in the category of topological spaces. Okay, and I ask you, is X the real numbers? Okay, so this is like going to be part one of my game. So is X the real numbers? Now, the only information that you have is this object X, the category, the abstract category of topological spaces, and you also have whatever you are calling the real numbers. And if you want to check if the X that I gave you is the real numbers, I would accept as a solution finding an isomorphism between X and R, or maybe not, in which case it's not the real numbers. Okay. So just to detail what I'm trying to say here is that when we consider objects in the category of topological spaces, we can give them labels. We can label it as the real numbers. But the interpretation as such of the real numbers is actually something that we are doing. So let me show you a little picture. So can you guys see this? Hopefully you can.
Yeah, we can see it.
Okay. So here is a little sample of a swath of the category of topological spaces, okay? And you can see inside of here that we have an R, and we have the X that I gave you, but we also have every other topological space. Now, from your perspective, you're looking at a bunch of objects, and you see that there's R2 in here and R3 in here, and you know, the paths into R2 or the circle or the sphere or whatever is inside of here. But you're labeling it in terms of what you know about the objects. So from your perspective, this category has a bunch of labels that you know how to interpret. But from the category's perspective, this is what it looks like. So, you know, the category has no idea what the objects actually are. All it knows is that there are objects, that there are morphisms between them, and how to compose those morphisms, and also whether or not a morphism is the identity. So you can check the isomorphism classes to check whether or not X is isomorphic to R, but you can't really check whether or not X is R. So let's go back to this note. So let's try another version of this game. Okay, so I'm going to give you another category. So I'm going to give you a category S. It's going to be a small category. And in that category, there's going to be 3 objects, 2 of which I won't label, and 1 that I will label R. Okay. So actually, I'm not going to label it just R. I'm going to label it R in top. So a couple of notes. First of all, the label R in top, despite your projections onto that label, is just a label. Okay. And so now my question is R in top, this object that I labeled like so, the real numbers? Okay. So now you don't have the category of topological spaces to do this sort of comparison for you. One thing that you can try is you can try to give a functor from S into top, and then you could do what you did before. You can ask if J of this object, which I labeled R in top, is isomorphic to the R that you actually know. Okay. However, this J was not given. Okay, it was chosen by you. So chosen by you. Okay. So the construction of this J not only relies on your knowledge of category theory, but your ad hoc construction. And ad hoc in that there are potentially other functors that would work or not work in deducing whether or not this object is really the real number. Okay, so just to really hammer in this this idea of choice, or this idea of like an ad hoc construction, let me give you a third category. And this third category is going to be pretty wild. So it's going to look exactly the same as the S I had above, except I'm going to give everything labels. So in this category, one of the objects is Z in ab, okay? So that means nothing other than a label that I gave it. R in top, and let's say R adjoin X in R mod. Okay, and it's okay if you don't know what any of these words mean. In fact, that's probably better that you don't know what these words mean. And I'm going to label this morphism n goes to n, and I'm going to label this morphism p of x goes to 0. Okay. So just like before, the labels that I gave this are legal. They're just strings. They're some crazy symbols. The interpretation is on you. The interpretation is not part of the category. Okay. And so the question is this the actual abelian group is the R in top, the actual space is this map that I called n to n, the actual function that sends the integer n to the real number n, okay? So that's the game that we're playing. We're trying to see if these things are actually what we say they are. And the way that you could do this now, we have 3 different categories that we're talking about, and the functions between them are not in those categories. They're actually in the category of sets. We could do some crazy construction. I could give you a functor now from S into this, what is called a comma category. And I'm not going to really go into this, but the point is that this comma category has objects from abelian groups, topological spaces, and R modules, and it has functions between the underlying sets of each of those objects. And so this category does well to interpret abelian groups, topological spaces, and R modules accordingly. But this is rather complicated. Okay, so, and it also has to do with the fact that I know about comma categories. And I know that, you know, maybe I can construct this functor into here. I chose this specific functor. Someone could have chose something else. Someone could have chosen a different category to interpret all the objects in S. And so there's a lot of choices that are floating around here. And these choices are all to ask whether or not the labeled objects in our categories, in our category S, are actually what we say they are. Okay. So in both of these, so in 1, okay, top interpreted X, and that seems like it's benign enough. But in 2, top interpreted R, but so did we. That choice we made was us interpreting what R is supposed to be. Okay. All right, so is there any questions about what I'm trying to get out here? Okay. So I can call a category an ontology. Okay, so what does that mean? So that just means that I have data and I have relations between those data. And that's perfectly fine. But I want to make a distinction. So I'm going to redefine ontology to mean something even more than this. Okay? So in a category, I have this data and I have these relations. And in an ontology, I'm gonna ask a little bit more. So I'm gonna have data and I'm gonna have relations, but I'm also going to have interpretations. Okay? So let's see how to do this. The way that I want to do this, so really the main goal here is to bridge together logical construction and ontological construction. Okay. So the way that I'm going to try to do that bridge is I'm going to interpret an object X in whatever category we have as a category itself. So let's see some examples of this. So let's try this with topological spaces. So I have an object or a space in the category of topological spaces. Okay, and I want to capture all the data of X in terms of a new category. So capture all data of X in a new category. All right, so let's see how we might do that. So I'm going to call O of X. This is going to be like our ontological interpretation. Okay. O of X is now going to be a category, so I'm going to describe to you what its objects and morphisms and so on are. So what is the data of a space? Well, it's the points in the set, and it's the open sets in the topology of the topological space. Okay, so these are the objects. It's you're either a point or an open set. And then I'll have some morphisms. So either my point is in a open set, or my open set is included in another open set. So those are the two types of morphisms in this category. And then finally, I have a composition. And the way that we're going to do that is if X is in U, and then we have U is in U prime, then the composition of this is going to be X in U prime. That seems to make logical sense. If X is in a set and that set is a subset of another set, well, X is in that larger set. Okay, so this is what we're going to do for top. Let's try it for groups. So we'll have a G in group. And I'll do the same thing. I'll have like an O of G. And the objects of this O of G are going to be tuples. So I'll have tuples as such. And this is going to be in G to the n. The morphisms are going to be like multiplications. So I have my tuple as follows, and then I go to a smaller tuple by multiplying a bunch of things together. So I go to xi, and then now I have multiplication up to xi plus k, and then I have xn. Okay? And the composition here should be obvious. I don't really want to write out a bunch of stuff, so I'm just going to write associativity. So what that means is if I do one multiplication and then another, it was as if I did all of it at once. Okay. So let's see what our category S that we were trying to describe is. So let me rewrite it here. So we had S, and this was defined as Z, and then we had an R, and then we had an R join X. And then we labeled this n goes to n, and we labeled this p of x goes to 0. Okay. So what we're going to do is we're going to interpret everything at once. So this sort of caret here is going to be for interpretation. So I'll draw a little O below it. And essentially what we're doing is we're expanding everything into categories. So here is going to be my O of z. And inside my O of z is maybe a tuple 1, 2, 3. And that maps down to 1, 6, which maps to 6. Okay, and then there's also another map here. Okay, there's obviously tons of other stuff in this, but I'm just trying to give examples. And now for R, we do the ontological interpretation that we have up here for topological spaces. Okay, so we'll have, for example, 6, and we'll have 0, and we'll have the ball of radius 1 around 5.5, whatever. And 6 is part of that ball, that open set. And 0 is, part of some other ball. We'll say b epsilon of 0. And sorry if this is really small on your screen. Okay, so obviously there's a lot more inside of this category, but again, I just want to give a little picture of what's going on. And finally, I'm going to expand this R module, and I didn't say anything about it, but that's because it's really tedious, but it's essentially the same thing. So here I'm going to have maybe a tuple p of x and q of x, and that's going to map down to p plus q of x, and then maybe I have a p of x also, and a q of x also. And so here I have the 3 expansions of the 3 different objects, or 3 interpretations of the 3 different objects in my category. Okay. And now the question is, how do I interpret the morphisms? So how do I interpret O of n goes to n, and O of p of x goes to 0? Okay. And I'm going to just draw it, and then I'm going to explain it a little right afterwards. Okay. So what I know about what n goes to n should do is, well, it should send 6 to 6. So I'm going to draw an arrow that's reaching this barrier, and that's for a reason. And then on this side, I have the function, or what this function is supposed to do is it's supposed to send all of these polynomials to 0. So I can send this one to 0, this one to 0, and this one to 0. So I'm going to call this my ontological interpretation, or ontological expansion, as I'll soon call it, of n to n. And this I will call my ontological expansion of P to 0. Okay. So before I get a little bit more technical, what I'm trying to do here, so really this is the goal, is to give a prepackaged way of interpreting data in an ontology. Okay? So a category is a form of ontology. These O of Z, O of R, these are interpretations. And so I want to package the category and their interpretation together.
So,
okay? Yeah.
So do the morphisms give functors between the categories associated to each object, or are they just assignments?
No, so I'll say something about that in a second, actually. Yeah. But I'm glad that you guessed that, because that is really the first guess, but it's not true. Okay. So now I want to make this clear. There is still some human interpretation going on here. So for example, the number 6, we know what 6 is, but the ontology, the raw ontology, does not. But there's nothing stopping us from continuing to expand. And we'll get to that later. Okay. So here's the question that was just asked. I think that was that John?
Yeah.
So the question that I want to ask is, well, what is O? Okay. So the first guess, well, for example, O of Z is a category. So we can guess that O is going to be a functor from S into the category of categories. And the point is that that's not true. And one of the easiest ways to see this is that a lot of the data is not being used. So not true. And for example, if you look at O of Z, the element 1, 2, 3 does not have an assignment. Right? So, I mean, just from sort of technical reasons, this is not a functor. You might also guess that maybe this is some sort of natural transformation. Okay. But that is also not the case, and I'm not going to go into that too much. What this ends up being is a submorphism. Okay, so let's talk about that. Okay. So, hold on a moment. Okay, so I'm going to try to describe to you what a submorphism is in general. But before I do that, I want to paint a picture of ontology. So paint a picture of ontology. Okay. So I've already distinguished categories from ontologies. And that distinguishment came from the fact that categories have no interpretation and ontologies should. So instead, I'm going to say that a category is a basic ontology. Okay, and that word basic means that it's only one layer. No interpretations. And the word ontology just means that it's organizing data. So let's give some examples of basic ontologies. Okay, so first we'll have a set. This is sort of the primordial basic ontology. In a set, you can organize data. There's no relations or anything, but you're housing data. You might also consider a graph. Like we talked about, we're going to consider categories. But in a minute, I'll say why we're actually not going to consider categories, but rather we're going to consider simplicial sets. We could also talk about n categories. This is some more expressive version of a category. And also we'll consider these as n simplicial sets. Okay, can also think about some other categories, let's say posets, so an ordered set. Just to give an example of why these would be used as a category, maybe a set and a poset would be used as a grocery list. Okay, and that's fine. We're organizing a bunch of data. Maybe this graph is used as a dependency graph for programs. So it's organizing programs and their dependencies. Okay. Obviously, categories, for example, we could be organizing the category of topological spaces. Let's keep going. We can be using groups as ontologies. So for example, I could be organizing the automorphisms of some space. I could be using semi-groups, or actually I should say monoids as ontologies. And maybe I'm considering the ideals of a ring. Okay. I could be using vector spaces. And maybe an example of this is like word embeddings. Okay. And even topological spaces themselves. So on the one hand, for categories, we're organizing topological spaces, but I could use a single topological space as a means of organizing other data. And if you've heard of, I think that this is the right word, the Teichmuller space. It's like a space of spaces. There's a lot of other examples of spaces of spaces. I could be looking at infinity groupoids, and I'll wrap this up in a second. Maybe I'm organizing like paths of a space, and I could also be looking at like infinity n categories. And this is the real thing that led me to considering ontologies, is the study of infinity n categories. Okay, so what do these all have in common? Well, first of all, they are all categories, but some of them have some extra structure. And that extra structure is that it's not just a category, but it's a category of functors. So we're going to say that a basic ontology is a functor B from some small category into some large category. Okay. And so what do these two bits of information buy us? Well, the delta tells us how to organize things, and I'll give you an example in a second. And the C tells us what we can say about the things. Okay, what propositions we can make. So for example, let's look at simplicial sets. A simplicial set, in a simplicial set, this delta is a specific type of category. It has the objects just natural numbers, 1, 2, 3, and it has morphisms, which I'll get to later. Okay. And just to paint a picture for those of you who don't really see the significance of categories and functors, I'll tell you that a simplicial set is a collection of sets. So for each of the natural numbers, we get a set. And for 0, we're going to have just a bunch of points. And for 1, we're going to have a bunch of arrows. Okay. And independently, these are just floating around in space. For 2, we're going to have a bunch of triangles. And I'll draw a little sigma in there to show you that there's actually something filling that triangle in. For 3, we're going to have tetrahedrons, and I'm not going to go further than this. So I'll say that this is equal to tau. Okay, and so altogether, what I have is a simplicial set, which I can draw as follows. Okay, so let me erase this point. So I have the points from the 0th level. I have the arrows from the 1st level. And then I have the triangles from the 2nd level. And altogether, I have the tetrahedron from the 3rd level. Okay, and this goes on for all natural numbers. So you can see just from the way that I draw this that simplicial sets are very related to categories. In fact, simplicial sets are more expressive than categories. So let's sort of see what happens there. So we have a category. This has objects. This has morphisms. And this has composition. And it also has associativity. So what that means is that f of g of h is equal to f of g of h. Okay. And in a simplicial set, I have 0 simplexes. Those are my objects, quote unquote. I have 1 simplex, which are my morphisms. And I have 2 simplexes, which are supposed to denote when things compose. And I have 3 simplexes, which will tell me when things are associative. Okay? So in a simplicial set, none of these things need to exist. But in a category, these last 2 need to exist. So I have some freedom over what objects and morphisms are in my category and how they compose, but the fact that they compose, the fact that they always compose means that that composition is always in the category, and they're always associative, okay? Whereas in a simplicial set, I can say that I have two arrows that don't necessarily compose, even if they're composable. Okay. So from now on, I will treat categories as simplicial sets. Okay, simplicial sets are looser than categories, but they contain all the data that is necessary to describe a category. And the reason that I will move away from treating categories as ontologies and instead treat simplicial sets as ontologies is that category theory is the meta language. Okay, and so if I am using categories to organize categories instead of using categories to organize simplicial sets, then that distinction wouldn't be made and it becomes very confusing. And in fact, it's sort of a confusion that happened earlier before when we were treating or trying to treat the ontological interpretation as a functor. It's not a functor. And if we were talking about simplicial sets, it might actually be a little bit clearer what it is. Okay, it's more combinatorial. It's not as natural. Okay, so category theory is the meta language, and simplicial sets I will treat as ontologies. Okay. So let's talk about some morphisms. All right. So we have our simplicial set, which I drew above, but I'll sort of simplify it here. So I have some objects, some morphisms, and a two-simplex that's showing that those things compose, and then another morphism that's just going out there in the middle of nowhere, and it doesn't compose to make another two-simplex. Okay, so this is just an example of a simplicial set. Okay, if I wanted to look at a sub-object of the simplicial set, what I need to do is I need to look at every single level and make sure that all of the subsets are at least closed under the fact that they contain their relevant faces. Okay, so in this case, this would be a sub-object of sigma, and that's because even though it doesn't contain, even though it doesn't contain this morphism, it contains everything that is relevant to sigma. Okay. So I'm going to call this S0. I'm going to call this sub-simplicial set S0. So S0 is a sub-object of sigma. It is also a zero submorphism of sigma. Okay, so the zero submorphisms are just sub-objects. I can look at my sigma, my original sigma, and I can restrict it below by everything of dimension 1. So what that's going to look like is I'm going to be throwing away the objects, and I'm just going to be looking at the morphisms and potentially the compositions. Okay, so here's this restricted below. And now I can look at a sub-object of this restricted simplicial set. So I'll call this S1. And we'll do something like this. Okay, so S1 is a sub-object of the restricted simplicial set, and S1 is a one submorphism of sigma, not restricted. So I can either think of a one submorphism as some sort of data associated to sigma, the full sigma, or I can think of it as a sub-object of the restricted simplicial set. Okay, and I can continue to do this. So I can restrict below by 2 now, and now all I have is the sigma. And so maybe the subset that I want to look at is just, well, the empty set. So I'll say S2, and, well, I think maybe you get the picture. So S2 is a sub-object of the restricted simplicial set, restricted down below by 2. And so S2 is a 2 submorphism of sigma. Okay. All right. So let's see what we can do to relate this back to what we're trying to describe. So remember, we're trying to describe the ontological interpretation that we had before. So let me just zoom back here and grab the picture that we had. Don't have to redraw it. Sorry if that made anyone dizzy. Okay, so the question is, what is the O in each of these levels? Well, what we see is that O associates to the 0 simplexes. Okay, it spits out a 0 submorphism. Okay, so for every object, quote unquote, it spits out a simplicial set. For every one simplex, so for every morphism, it's going to spit out a 1 submorphism. Oh, wow, I'm running out of time. Okay. So, so what's happening here is that the O of n, so this guy here, this is not a functor. This is not a natural transformation of simplicial sets. It is a 1 submorphism. Okay. So in general, what an ontological expansion will do, so I'm going to call it an ontological expansion. Okay, and this is analogous to the ontological interpretation. So we're expanding it to interpret it. Is defined as follows. So we have 2 basic ontologies, B and B prime. These are basic ontologies. Okay, and maybe just to be super simple, I'll still talk about them as simplicial sets. And an ontological expansion is a bunch of maps for each n that sends B of n. These are the n simplexes to SMB of n. And I'm just going to call these the n submorphisms. Okay. And there's a naturality property for those of you who have a keen eye. And what that means is if I look at a simplex that I want to expand, then here I have a face, another face, and this is the simplex. This expands to something that goes between the ontological expansion of the faces. Okay, so if simplex goes from one face to another face, then the ontological expansion goes from the expansion of the face to the expansion of the face. Okay, so finally, let's talk about ontology. We've been talking about basic ontologies. Let's talk about ontology. So there is a category. Okay, and now I'm using the word category, and so I'm talking about the meta language here. Okay, and I'm going to call this category ont, O-N-T. And the objects of this category are basic ontologies. Okay, so simplicial sets, or just sets, or lists, or whatever. The morphisms are ontological expansions. Okay. And the composition, I'll just draw a picture for this. Okay. So if I have one basic ontology here, so I'll say B, and I'm expanding that into another basic ontology, and expanding that one into a third basic ontology. Okay, so this is the categorical level. Okay, at the ontological level, I have a picture that looks something like this, and I'm expanding into another ontology, and I get some sub-ontology, and then I can expand this even further into a third ontology. So it looks something like this, and this one expands so. And there's some maps here and some morphisms there. And so the composite expansion is just, whoa, okay. Sorry. The composite expansion is going to be the expansion that looks at all the expansions at once. Okay. And of course, I'm avoiding a lot of formalisms here, but I want to give the idea of what I'm trying to describe, not necessarily the formal language. Okay, so this red would be the composition O prime of O. Okay. All right, so I'm going to wrap up here. I'm not going to be able to talk about some of the real applications of this, unfortunately, but I'll just mention them. Okay. So the question is, what are these used for? What do ontologies buy us? And the first thing that I want to make very clear, I haven't yet defined an ontology, so let me just do that very quick. So definition, and ontology, which we'll just have as a little blackboard O, is a subcategory of ont. Okay. So let me give some examples of this, and then I'll say why it's useful. Okay. So I'm going to give an ontology, and it's going to be an email I received. Okay. And in this email, Well, you know, at one level, it's just an email, but I can give it an expansion, and I got this huge, huge block of text. Okay, and I really don't want to read it, but I have to, and so I read it, and I'm trying to parse it. Okay, trying to understand what's going on here. So what I do, if I'm trying to take this ontological perspective, is I want to create more levels, more hierarchical levels of this ontology. So in this email, there are probably some very important high-level ideas. Okay, so I'll say there's a number of those. And for each of those high-level ideas, there are some mid-level details. Okay, so maybe this is something that my boss is telling me to do, etc. Okay, so there's a bunch of expansions here. And my boss didn't include how to actually do them. So for me to understand what this email is about, I now need to add some implementation details. Okay, so I'll just have a bunch of those. Now, what this sort of buys us, what this buys the non-perfect data organizer, I'm not a computer, and so if you send me a bunch of data, I'm not going to be able to understand it all at once. What an ontology buys us is one paradigm for high-level and low-level ideas. Okay. So let me give you a concrete example of this, and this goes back to the ontology that we associated to a topological space. So here we have a topological space, and here we have all of the points of the space, you know, so X, Y, and Z, and all the open sets, U prime, union U prime, whatever. Okay. So at this level, this is like the implementation level. And at this level, this is the most abstract label. And I want to understand what is relevant in between the abstract label and the implementation. So before I get to the full details of what X is, I might want to stop halfway to distinguish different parts of X. Here I have the underlying set of X, and here I have the open sets of X. And the underlying set of X maps into the open set of X in some way that I don't necessarily know. Okay, so here's this expansion and this expansion. But what the submorphisms tell me is, well, the points of X are these X, Y, and Z. The open sets are this U and U prime, etc. And this map here, this vague map that I'll just call is in, which is not well-defined at all, becomes well-defined when I start to associate different objects in this zero submorphism to this zero submorphism via a one submorphism. So what is this doing? I'll try to finish up right now. What this is doing is making vague relations concrete. So at this relevant level, the is in relation that I drew here is not well defined. It's a vague relation. But once I expand it into the submorphisms, it becomes well defined. Okay, they're actually inclusions. And so I can do this with really anything. And this is the final example. I'll end on this. I can do this with really anything. And I love giving this example. So there are three people. There's Alice, there's Bob, and there's Noah. And Alice is friends with Bob. And Bob is friends with Noah. And I'm trying to deduce what the relation is between Alice and Noah. And I'm assuming that there is some way that I can deduce this relation from the given friendships. Well, nothing here is well-defined. Alice is not well-defined. Bob is not well-defined. Noah is not well-defined. Friend is not well-defined. But I can attempt to expand everything and see if I can interpret it a little bit better. Okay, so inside of Alice, well, there's her brain, and there's her phone. Okay, and her brain is connected to her phone. Okay, it's speaking through her phone. And in Bob, he also has a brain. He also has a phone. His phone speaks to him, and he speaks to an email. And inside of me, I have an email, and I have a brain. Okay, and something that is maybe a little bit more concrete is that her phone is talking to Bob's phone. So I'll say call. Okay, and so her brain is talking to her phone, and so her brain is talking to Bob's brain. Likewise, his email is talking to me, and therefore his brain is talking to my brain. And finally, we can show through this giant composition that, that her brain is talking to my brain via Bob's brain. Okay, so on this level, there is only one simplex. So let me just write stuff in here. So the email is emailing my email. And so there's this sort of message passing that's happening between our brain. And there is only one simplex here. So I'll call this simplex message. I'll call this message as well. Message. Okay. And so it becomes clear that, or clear to us, that the interpretation of this composition of friendships is really just the composition of message passing. Okay. All right. So I think I'll end there.